Hi, I'm glad you're here. You're just in time to enjoy another video on thermometry. And in this particular video, we're going to talk about exposure standards. The exposure standard that we're going to discuss in this video deals with moving platforms. If you have a thermometer on something that is moving, and when you have, or when you're trying to measure temperature, you have to be concerned about the airflow past the thermometer and what type of temperature are you measuring. In aviation and in other disciplines, we define two different types of temperatures, either static air temperature or total air temperature. Static air temperature is the temperature of the air, what you normally want to measure if the air is moving very slowly. This is our normal measurement of temperature, static air temperature, or SAT. SAT assumes that there is some air flowing around the thermometer, but the speed of the air is rather slow. And there are some advantages to having wind flowing past the thermometer. Of course, it increases the convective heat transfer and reduces the sensor error. But if you're moving very fast, let's say if you're moving 200 or 300 miles per hour, then you start to have compression against the thermometer bulb. In other words, the air slows down and it warms adiabatically. And that is transferred to the thermometer, and the thermometer will read fictitiously high. We have a temperature we define as total air temperature, or TAT, which is the temperature moving air would have if it were slowed to the stagnation point, or to stagnation, through adiabatic compression. So ahead of an airplane, let's say we're flying an airplane trying to measure temperature, ahead of the airplane, you have the air moving at a certain velocity as the airplane approaches it, relative wind in aviation. As the air approaches the wing, it will slow down to the point where the velocity is zero. All of that energy goes someplace, and it goes to raise the temperature of the molecules of air if the air doesn't flow over the wing. Right at the stagnation point at the leading edge of the wing, that's where you see adiabatic compression. And of course, any other object on the airplane that's sticking out will also see adiabatic compression. There are certain type of special thermometers that measure temperature on airplanes. Total air temperature gauges have a specially designed recovery factor. What recovery factor is, it's the ability to completely convert the kinetic energy of the moving air to the adiabatic motion of air molecules. In other words, recovery factor is how well the thermometer slows the air down to 0 miles per hour. Thermometers are specially designed. It takes lots of thinking, lots of aerodynamic testing to come up with a thermometer that has a very high recovery factor, meaning that it completely slows the air down and you get a rise in temperature. Because if you can completely slow the air down, if your recovery factor is 1, there is an equation that converts total air temperature to static air temperature, from TAT to SAT. So in a moving airplane, we measure TAT, but what we would really like to know is what is SAT, what is the static air temperature. And of course, this depends upon the speed of the airplane. Airplanes moving that fast usually measure speed in Mach number. And Mach number is the speed of the aircraft divided by the speed of sound. So our equation here shows static air temperature is equal to total air temperature divided by 1 plus 0.2 times the recovery factor times the Mach number squared. If the airplane is moving through the air and moving at a good clip, total air temperature is always going to be greater than static air temperature. So that gives you a little bit of insight into trying to measure temperature from a moving platform.